Okay, in this chapter, we'll go over chemistry and measurements. Now, in addition to assisting physicians, registered nurses, like the one you see here in the picture, work to promote patient health and to prevent and treat disease. As you can imagine, measurements are a key role in their job and also in chemistry in general. So, as you can see here, she's checking this man's blood pressure. I will begin with basic units of measurement. Now, in a great majority of the world, the metric system is the standard system that's used for measurements, and mostly because it's far easier than what we use here in the United States, the English system. We're one of only a few countries in the world that still use the English system. But the metric system is based on powers of 10. So it's much easier to convert one unit to another because they're all based on this multiples of 10. All right, so for the learning goal of this chapter, be able to write the names and abbreviations for the various metric or the international system units of measurements for length, volume, mass, temperature, and time. So in this picture, you have the two students walking most likely to class. The temperature 22 degrees Celsius, which would be equivalent to 72 degrees Fahrenheit. The backpack here, 12 kilograms or 26 pounds. This person's height, 1.65 meters or 65 inches. This person's weight, 58.2 kilograms or 128 pounds. And they are walking 2.1 kilometers or 1.3 miles. So all these are equivalent values to each other. This one's in metric, one's in English. Metric, English. Now, scientists throughout the world have used the metric system for measurements, and there's a slight modification of that metric system. It's called the International System of Units, or SI units. And there's very little difference between the two. There are some units that are slightly different, but we'll get into some of those here in a few minutes. But these are the units that are used throughout the world scientifically for measuring length and volume, mass, temperature, and time. All right, here are some of the more common ones. This column here is what's used in the metric system, and this column here is what's used for the international system of units. For the standard unit of length for the metric system is meter, abbreviated by the lowercase m. Also for the international system unit is also meter, the lowercase m. And something I'll mention now, be careful when you are writing these abbreviations for these units to use lowercase when you're required to use lowercase and not capital. You can't go back and forth interchangeably because a capital M means something very different than meter. And we'll talk about that a little bit later on in this chapter. But lowercase m is always for meter. The standard unit of measurement for volume for the metric system is liter, or capital L, or in the international system is going to be the cubic meter, m to the third power, a cubic meter. Now, liter is probably the only measurement in countries that use the English system, like the United States, that is used most often. So you can buy a 2-liter or 3-liter soft drink at a grocery store. That's probably the only one that, as Americans, we are most familiar with as a metric unit, is liter. The common unit for measurement for mass and metric system is the gram, represented by lowercase g, and then the SI units, the kilogram, a kg. All right, for temperature, for the metric system, it's degrees Celsius. Degrees in a capital C for Celsius. And for the international system, it's called Kelvin. And we'll talk about that a little more later. And then the unit of measurement for time is the second, or lowercase s. And that's true for both SI units and metric. So you will see these abbreviations quite often when it comes to chemistry, especially when we get to the chemical equations and how to use them. All right, the length in the metric and the SI systems is all based on the meter, which is just slightly longer than 1 yard. So for here, 1 meter is the same thing as 100 centimeters. You remember centi or cent. You think of cents in a dollar, there are 100 of those. So the prefix centi always means 100 of, or 100th. 1 meter is also 39.4 inches. It's also the same thing as 1.09 yards. And then 2.54 centimeters is the same thing as 1 inch. So all these are equivalent values to one another. That is the same as that. That is the same as that. That is the same as that. And that is the same as that. All right, when we talk about volume, we'll be talking about the liter or the milliliter. Now, volume is a space that's occupied in 3 dimensions, both length and width and in depth. So the standard unit of measurement is called the cubic meter. And it's called a cubic meter because it involves 3 dimensions: length, depth, width. That's why measurements of volume are always in a cubic in dimensions. But in a metric system, the volume is based on the liter, which is slightly more than 1 quart. So we have some equivalent values down here. 1 liter is the same thing as 1,000 milliliters. 1 liter is also the same thing as 1.06 quarts. And 1 quart is also the same thing as 946 milliliters. And you see those measurements here on this image here of the graduated cylinder. Right there, about 946 milliliters equals 1 quart. So just under 1 liter. Alright, when we talk about mass, we'll be using the gram or the kilogram. Now, the mass of an object is its measure of quantity of stuff that it has, the quantity of material that's found inside that object. 1 kilogram is the same thing as 1,000 grams, because a kilo always means 1,000. So this word will literally break down into 1,000 grams, kilograms. 1 kilogram is also the same thing as 2.2 pounds. And 1 pound is the same thing as 454 grams. Alright, in the SI units for mass, you will use the kilogram, or kg. That's usually used for larger masses. And in the metric system, you'll use the gram, or lowercase g, which is going to be used for lower or smaller quantities of mass. Alright, next we'll move on to temperature. You'll be using either degrees Celsius or Kelvin. Now the temperature will tell you how hot or how cold something is. So for the metric system, you'll use degrees Celsius, and for the international system, you use Kelvin. Now water will freeze at 32 degrees Fahrenheit, and that's equivalent to 0 degrees Celsius. These are exactly the same temperature, just using 2 separate scales. Same thing with the boiling point of water. Water will boil at 212 degrees Fahrenheit, which equals 100 degrees Celsius. Those are equivalent temperatures, but using 2 separate and distinctly different scales. Now the Kelvin scale for temperature begins at the lowest possible temperature, the temperature called absolute zero, which is 0 Kelvin. That's equivalent to negative 273 degrees Celsius. And that scale we'll get into more a little bit later in our series of videos. Alright, next we'll talk about time. The unit for measurement for both the SI system and the metric system is the second. And then from there you can get larger and larger, but the base unit that you use is the second. So you can go anywhere from years to days to hours to minutes to seconds. So 60 seconds is 1 minute. 3,600 seconds is 1 hour, and so on. Alright, next we'll move on to the rules for rounding off values. Now, this can become very significant when you're dealing with measuring quantities, because you don't want to make a quantity too less important or too more important. So when it comes to rounding, the key number to remember is the number 5. So anything that's 5 or higher will be rounded up to the next number. If it's less than 5, nothing gets changed. So the key thing that you're looking here is to where you are rounding to. So let's say for this example, 8.4234. If you're rounding off to just having 3 significant figures, these first 3, you look at the very next one next to it. This number 3 is less than 5, so nothing will change to that number. So 8.42. Everything else gets cut off. If you're rounding to just 2 significant figures, you'll have these 2 here, 8 and 4. The 2, same thing, is going to be less than 5. It won't change this, so 8.4. Okay, that's an example where nothing changes. But for this next one, things do change. The number you're given is 14.780. If you're running that to 3 significant figures, 1, 4, and 7, you look at the number just next to that one, 8. 8 is higher than 5, so that's going to cause this value to go up 1. So this number will round off to 14.8. Everything else behind that 8 is dropped. If you're rounding this number to the nearest whole number, or to just 2 significant figures, 1 and a 4, again, the 7 is going to be higher than what you need. That's going to cause this value to go up in 1, or that rounds up to 15. So it all depends on what place value you are rounding to. You look at the very next column to the right. Is that value 5 or more? If it is, then the last place you round to will go up by 1. If it's less than 5, then nothing changes. Alright, next we'll move on to prefixes, something that's going to be very important, and understanding some basic prefixes will help you understand chemistry a lot faster, because the key thing about prefixes is their definitions never ever change definition. Doesn't matter if you're talking about chemistry or physics or biology or anatomy. Kilo always will mean 1,000. Centi always means 100th or 100 of. It doesn't matter if you're talking about grams or meters or liters. Those definitions never ever change. So in some prefixes you will see much more commonly than others, like milli, micro, kilo, centi. Those you will see quite often. There are some that will pop up on occasion depending on what you're working with. But if you are familiar with some of the more common ones, being able to convert from one unit to the next gets quite simple. So for example, the ones that are given here, milli and micro, these are usually fairly common, especially in a chemistry setting or a nursing setting. Milligram or milligram, either way to pronounce it is fine. This word literally breaks down into 1,000th of a gram. Milli will always mean 1,000th. Microgram always means 1,000,000th of a gram. So microgram or micron, those terms are interchangeable, especially when we get to anatomy. Now you'll see here this has 2 abbreviations listed for microgram. That's because in medicine and in anatomy you'll see microgram used quite often, and the way you write micro looks like a lowercase u that's in italics with a small tail right here. It's very often misread when a person writes it as opposed to a computer typing it like you see here. But it's very easy to misread that because it's hard to write it correctly by hand. So another way to write microgram is also mcg, or microcentigram. So these two are equal. It just depends on if a human is writing the value or not. Here are some prefixes for some of the larger values. We'll start here, then work our way up. So kilo, prefix kilo, always abbreviated by lowercase k. That means 1,000. Also represented by 10 to the third. There are 3 zeros here. So that's why the exponent is the number 3. So kilogram, 1,000 grams. Kiloliter, 1,000 liters. Kilometer or kilometer, 1,000 meters. Definitions never ever change. Mega, capital M, not lowercase m like you saw for meter, but a capital M always means 1,000,000. There are 6 zeros here in that value. That's the same thing as 10 to the 6th. Giga, capital G, means 1 billion. Again, there are 9 zeros in that value. So that quantity is 10 to the 9th power. Then tera, capital T. Then peta, capital P. And you'll see the corresponding values here, 10 to the 12th and 10 to the 15th here. So for those of you who are fairly familiar with computer measurements, a megabyte is 1,000,000 bytes, gigabyte, 1 billion bytes, and you get the tera, then peta, and so on. So it doesn't matter if you're talking about computers, or human anatomy, or physics, or chemistry, these prefixes never ever change their definitions. Alright, those were some of the larger prefixes, or larger values. Now we'll go the other way, getting smaller. Deci, lowercase d, that means a tenth. Deci, think of decade, there are 10 years in decade. That's how you get to 1/10, or 10 to the negative 1. Centi, lowercase c, 100th, or 0.01, or 10 to the negative 2. Milli, 1,000th, 0.001, or 10 to the negative 3. Micro, and that's the reason why it has that asterisk here. It's explained here. In nursing and medicine, it's easily misread when handwritten. So when you see it on a computer screen, you'll see it like this. If you see it handwritten, you'll usually see that, mcg. Same equivalent value, just 2 different ways to express it. That will mean 1,000,000th, or 10 to the negative 6. Not 1 million, but 1,000,000th, because we're talking about fractions of a whole. Nano, 1 billionth, so 0.000000001, or 10 to the negative 9. And then pico, 10 to the negative 12, and femto, 10 to the negative 15. So of these, when you talk about chemistry, we talk about human anatomy, you will probably see the first 5 of these most often. from nano, micro, milli, centi, and deci. If you're dealing with physics, then you'll get into pico and femto. Alright, prefixes and equalities, something we've already mentioned briefly already. Alright, the relationship that a prefix has with its unit can be expressed with this numerical value. Think of the prefix as the first name of the value. Just like we talked about before, kilo always means 1,000. So a kilometer or kilometer, 1,000 meters. Kiloliter, 1,000 liters. Kilogram or kilogram, 1,000 grams. And there's some equivalent values here, each of those. But again, definitions never ever change, regardless if you're talking about mass or volume or length or whatever. These definitions for the prefixes never change. Alright, next move on to the cubic centimeter. Cubic centimeter is abbreviated by cc, cubic centimeter, or cm raised to the third power. It's a cubic measurement. You're talking about a three-dimensional measurement, length and width and depth. So that's why I say cubic description, because you're talking about volume. Now, a cubic centimeter is exactly the same thing as a milliliter. So these three values here are equivalent. So 1 cubic centimeter is the same thing as 1 cc, the same thing as 1 milliliter. So it's important to keep that in mind, especially if you're talking about medicine and administering drugs. As you can see in the picture, this person is giving a bag full of medicine, and it says it's 1,000 milliliters. That value is exactly the same thing as 1,000 cubic centimeters, or 1,000 cc's. Right, on this image, you will see a graphical representation of a cubic centimeter. If you were to envision a cube that's 10 centimeters long, 10 centimeters deep, 10 centimeters wide, 10 times 10 times 10 gives you that 1,000 cubic centimeters, which is exactly the same thing as 1,000 milliliters, exactly the same thing as 1 liter. These three values are equivalent. This is represented three different ways using three separate units, but the actual quantity being measured is exactly the same. All right, next move on to measuring mass. Visit a doctor for any kind of exam. You are usually weighed shortly after you get there. Your mass will be recorded in either pounds or in kilograms, most likely in kilograms. And then various lab reports are usually reported back in micrograms. All right, below here are some equivalencies between different measurements. 1 kilogram, like we talked about before, 1,000 grams. Same thing as 1 times 10 to the third power grams. 1 gram is 1,000 milligrams. 1 gram is 100 centigrams. So again, all of these are going to be equivalent to each other. That equals that, which equals that. That equals that, equals that, and so on. Here are some common equalities, both for the metric system and then what we use here most often the English system in the US, and then the equivalency between those two. 1 kilometer is 1,000 meters, 1 meter 1,000 millimeters, and so on. 1 foot in the US equals 12 inches. Let's see, 1 yard is equals 3 feet. 1 mile is 5,280 feet, and then below are the measurements for mass and volume and so on. So you can see where the English system, or what we use here in America, is difficult to learn and difficult to follow for most aspects, because it doesn't follow a discernible pattern. There's no increase by 5 or increase by 10. There's always a weird number associated with each value. 12 inches in 1 foot, 3 feet in a yard, or 5,280 feet for 1 mile. There's no pattern to it, which is exactly the opposite for the metric system, where everything is based on a power of 10. 10, 100, 1,000, 1 100th, 1 1,000th. It's all based on just moving a decimal place, either left or right. For the English system, it gets a lot more confusing, so it's very easy to get confused when you're trying to express different measurements in different units. And this last column has the equivalencies between the metric and the US system. 1 inch is equal to 2.54 centimeters. 1 meter is 39.4 inches. 1 kilometer or 1 kilometer, same thing as 0.621 miles. And there are other equivalents here. 1 liter, 1.06 quarts, 1 kilogram, 2.2 pounds, and so on. Alright, next we'll talk about the chemistry linked to health and toxicology. Alright, as new chemicals are being developed and tested, one thing that has to be always taken into consideration is, at what level is this chemical not safe to be used? And unfortunately, that has to be tested. That's why testing on animals is such a key role in developing chemical drugs or pharmaceuticals. Any kind of material that uses chemicals has to be tested to determine at what point people should not use it. That point is called the LD50, or the lethal dose. It's at that level of concentration that 50% or more of the test subjects are killed with being exposed to that substance. So LD50, that level of toxicity. So at that point and beyond, it will be toxic to humans. That's what's called the LD50, lethal dose at when 50% or more of animals tested were killed. Alright, so the LD50 for something like caffeine is 192 milligrams per kilogram of that person's body mass. To give you an idea of how large this quantity can be, a male that weighs 175 pounds, that equals to about 80 kilograms, 80 kilos. So that person's LD50 would be 80 kilograms times 192, or 15,272 milligrams. That point and beyond would kill that male that weighs the 80 kilograms. But 15,000 milligrams is a very large amount of caffeine. And to give you an equivalent value, the 15,272 milligrams is the same thing as 15 grams of caffeine. So that'd be a huge amount of one substance to take in. So at that point, he's probably going to be dead from other things anyway. Alright, next move on to the topic of density. Learning goal for this section of this chapter, being able to calculate the density of any substance by using a formula that we'll go over, whether it be a liquid or a solid or a gas. Now, objects that are more dense or heavier in water will sink. Objects that are less dense will float in water. That's what you're shown here in the speaker. You're shown a cork, a block of ice, the water, a piece of aluminum, and some lead. The way you calculate density is the substance mass divided by the volume that it's in. So for example, the density for cork is 0.26 grams per milliliter. That is less than what it is for water. Water is always going to be 1 gram per milliliter. So the cork and the ice are less than that. That's why they float in water. The aluminum and the lead, their densities are higher than that 1 gram per milliliter, so they will sink. This equation will explain how many things will either float or sink when placed in water, all due to its density. If it's more than density of water, it sinks. If it's less, it will float. Alright, this table has some densities of some very common substances. Some we already saw in the last picture, the cork and the block of ice. Body fat, just slightly less than water, at 0.909 gram per milliliter. Bone, 1.8, so that would sink. So in this table, anything from muscle down would sink. And these are all solids. So you would imagine most of these would sink. The only ones that will not on this table are the cork and the body fat and the ice. But all these other values are going to be greater than 1. So that's why they will go down to the bottom of the container. For liquids, gasoline is 0.74, so that would float on water. Ethanol, or ethyl alcohol, would float, 0.79. Anything from this point on in the column and down would sink. Urine, just slightly heavier, or slightly more dense than water, so that would sink. Plasma, what comes from blood, milk, blood, mercury, all those are much denser than water, so that would sink. As for gases, as you'd imagine, a lot of these will be lighter, less dense than water. So of this column, hydrogen, helium, methane, and neon will be less dense than water, so they will float. And then nitrogen, air, oxygen, and carbon dioxide, from this table anyway, are the only ones that would be heavier, would be more dense than water, so they would sink. Alright, like mentioned on a previous slide, the formula for calculating density, the mass of the substance divided by the volume of the substance. So for a solid or a liquid, that can be represented by gram per cubic centimeter or gram per milliliter. The density of a gas is going to be a gram per liter. And the reason why for here you can represent these two separate ways, 1 milliliter is the same thing as a cubic centimeter. The last topic of chapter number 2 is called specific gravity. Now specific gravity is a relationship between the density of a given substance compared to the density of water. And the way you calculate specific gravity is by dividing the density of the sample by the density of water, which is 1 gram per milliliter at a temperature of 4 degrees Celsius. Now this value for specific gravity does not have a unit that goes along with it. You just get a numerical answer. For the units used in these calculations will cancel each other out. The formula for specific gravity, the density of the sample divided by the density of water. This is something that we will get into in greater detail when we get further along in this crash course on chemistry, when we deal with some very detailed chemical formulas and how to use them correctly. We will revisit this topic again in a future chapter. Thank you for watching our newest video on our crash course in chemistry. We'll have new videos in this lecture series
every Monday and every Friday of each week. So stay tuned for our next video in a few days. And don't forget to subscribe to this channel so you can be notified of when our new videos are posted each week.